In this video, we're going to look at a family of functions called power functions. Power functions are of the form f of x equals kx to the p, where k is some non-zero constant and p is a real number. I want to look at the four different possibilities for the end behavior or long-run behavior of a power function. So although k can be any non-zero constant and p can be any real number, I want to restrict our attention for k being 1 and p being even whole numbers. Here I'm looking at a popular website called Desmos, and I'm going to type in several examples of power functions where k is 1 and my exponent is a even whole number. So for example, look at the graphs of y equals x squared, y equals x to the 4th, x to the 6th, and x to the 8th. Notice as the powers get larger that the graph gets flatter near the x-axis. But what's important for this video is that the end behavior remains the same. As long as the value of k is some positive number, in fact I could have made this 2 or 3 or 4, as long as I replaced k with a positive number and replaced the value of p with an even whole number, I get that the ends of the graph both point up. So let me show you the notation that's used to say that if you were to trace to the left on the graph, that would be x values going in the negative direction. In fact, if you keep going in the negative direction, to the left that is, you can think of this direction as going on forever in the negative direction. We call that negative infinity. And as you trace along the graph to the left, your output values, f of x, go up in the positive direction because here's your function values getting bigger and bigger in the positive direction, 1, 2, 3. So we call that positive infinity. And it would be written as x approaches negative infinity. This would be the left end behavior because you're tracing to the left. The function values, f of x or y, are getting bigger and bigger in the positive direction, so we say that the function values approach positive infinity. Then, the right end behavior concerns itself with what happens as you trace to the right or let x increase without bound in the positive direction towards infinity. So as I trace to the right, letting x grow without bound in the positive direction, notice that your y values still approach positive infinity. So as x approaches infinity, my y values or my function values also approach positive infinity. Now note, if k was not a positive number such as 1, if I was to replace k with a negative number, you may remember that having a negative in front of a function reflects the graph about the x-axis. So instead of having both ends pointing up, they would both point down. This could be easily illustrated by simply putting a negative symbol on the outside of my previous four functions. If k was any negative number, notice that the end behavior of the graph is such that the ends of the graph point down, both to the left and to the right, as long as k is any negative number and p is some even whole number power. Now k could be any negative number, but for my example, I replaced k with negative 1, but the end behavior remains the same. So in a similar way, we can write the left end behavior using this notation. As x grows without bound in the negative direction, think of this direction as x getting larger and larger in the negative direction, meaning we're tracing to the left. And as x grows without bound in the negative direction, my function values or y values are going down, so they are getting larger and larger in the negative direction. And you can think of that direction being such that you're approaching negative infinity. So as x goes to negative infinity, your function values also approach negative infinity. And the right end behavior would be as x approaches positive infinity, meaning we're letting x get larger and larger, but this time in the positive direction, so we're tracing to the right, your function values get larger and larger in the negative direction. They approach negative infinity. Let's repeat these examples, keeping everything the same, except this time we'll let p be odd whole numbers. So now we'll let k be some positive number. I set it to be 1, but it could be any positive number. And let's look what happens to the end behavior when p is odd and is a whole number. So I'm going to change our exponents from 2, 4, 6, and 8 to 1, 3, 5, and 7. Notice the graph does change somewhat as p gets larger and larger. But as long as I have a positive coefficient and my power p is an odd whole number, the end behavior stays the same. The graph goes down to the left and up to the right. So the notation to basically say that the graph goes down to the left and up to the right is that the left end behavior would be, as we trace to the left, allowing x to get larger and larger in the negative direction, we say it's approaching negative infinity. My y values get larger and larger in the negative direction, which we denote as negative infinity. Then the right end behavior would be, as we trace to the right, allowing x to get larger and larger in the positive direction. So x is increasing without bound in the positive direction. My y values, or my function values, approach positive infinity, basically because when you go to the right, the graph goes up, which means your y values are getting larger and larger, but remaining positive. Lastly, if we kept all of this being the same, but replaced k with any negative number, I replaced it with -1 for this example, having a negative in front of our previous function would flip these graphs about the x-axis, and our end behavior would just be the reverse. This is easy to illustrate by simply going back here and putting a negative in front of each of my previous equations. So notice now, instead of the graph going down to the left, it's going up to the left. And rather than it going up to the right, it is going down to the right. This is easier to see when we compare what we had before to what we have now. These graphs are nothing more than an x-axis reflection relative to these graphs. So now, if we trace to the left, meaning let x get larger and larger in the negative direction, we're going to let x take on larger and larger values, but negative. And as we trace to the left and let x approach negative infinity, my y values grow without bound in the positive direction, meaning they approach positive infinity. This is what's called the left end behavior. The right end behavior would be where you let x approach positive infinity, and as x approaches positive infinity, or grows without bound in the positive direction, my y values, or my function values, approach negative infinity, and you can see this in the graph by simply seeing that as you trace to the right and let x go to positive infinity, your y values are going in the negative direction, and we say that they approach negative infinity.